All right, so let's look at an iceberg. It's often said that the upper 10% of an iceberg is all that you see. Let's do a little derivation of that based on the density of salt water and ice. So if we've got an iceberg, the only two forces that act on it, of course, are its weight, mg, and the buoyant force from the seawater, Fb. Now, the forces will be balanced because this thing is at rest. So the force of buoyancy will equal the weight. Now, rather than write a separate equation for fluids and then object density, I'm just going to substitute in for the force of buoyancy the expression rho GV. Now, rho is the density of the displaced fluid, which is seawater. So let's use an S for that. Seawater, this will be rho S. And then G is the gravitational field. V is the volume submerged. Now, how much of this iceberg is submerged? Well, it's not entirely submerged. It's only partially submerged. So let's let F be the fraction above. And that's what we're hoping to show is 0.1. So 1 minus F will be the fraction below. So F is the fraction, well, that's really messy. F is the fraction above, and 1 minus F will be the fraction below. Let's try that again. So F is the fraction, that's better, above, and then 1 minus F is below. So the submerged volume then is going to be a fraction 1 minus F of the total volume, V. Okay, so that's the buoyancy. Now let's get an expression for the mass. Well, the mass, by the density equation, we know density is a mass over a volume, and consequently the mass is density times volume, but it's the density of the ice. So this is rho I, let's say, for ice or iceberg. That times its volume times g, and this volume is the entire volume of the object. So we'll put density, maybe I'll write it out as ice, that's better. And I'll write this out as C. So this is the density of seawater here on this side. This is the density of ice. So these two must be equal to each other if it's floating, because this is the buoyant force and this is the weight. Now clearly the g and v cancel on both sides, and so we end up with this expression for the unknown fraction f, which is what we're looking for. So we want to isolate f, so we're going to divide both sides by rho c, the density of the sea, water, and then bring this over to the left, and I'll bring minus f over to this side to isolate positive f. And it's 1 minus the density of ice over the density of the seawater. So if we put in the values, what is it? 917 for ice, and then 1024 for the seawater, then we can calculate then the fraction f, and that works out to be 0.10 or about 10%. So 10% is above, and the other 90% is below, as expected. So this is another application of our analysis of buoyancy and buoyant forces.